Okay, so now we're still in 2.6, but now we're doing types of basic functions. So what I'm going to do is I'm just going to talk about the different types of basic functions. I'm going to talk about their domain, the range, where they increase and decrease, and where they are continuous. Okay, so first we have this function here, y equals x. That's just the equation, this is the function, and it's just a straight line. Okay, and it's a straight line, and we can call it a line, but its other name is called identity function. Okay, so you can say this is a line, or you can say it's an identity function. So because this goes on forever and ever and ever this way, and forever and ever this way, we say, what is the domain? Which means domain, I just put this here so you know domain. Domain is x. So we say, where does this function exist on the x-axis? Well, it's going to go forever, so it's going to exist everywhere on the positive side, and because it keeps going here, it's going to exist everywhere on the negative side of the x-axis. So the domain is going to be negative infinity to infinity. Now the range here, the range is where does this graph exist on the y-axis, or f of x. Because it goes up, 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 it's going to use all the positive y values, and because it's going down, 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 it's going to use all the negative y values. So the range is all of the y-axis, from negative infinity to infinity. So now we have to think of, I just need to grab a piece of paper. Okay, I'm going to draw a little person. Let's draw a woman in a skirt. Here's a woman. So she is going to go for a walk, and she always walks this way. If she's walking this way, this is her, she's walking up. It's difficult to walk up, especially after COVID, so she's walking up, 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 up. Walking up is increasing. So this line increases, and it's always increasing, so it increases everywhere. So we say it increases, and we're always talking about the x-axis. It increases all over, so negative infinity to infinity. Continuous. Continuous just means I can draw the function without lifting my pencil. Yep, I can draw it without lifting my pencil, so it's continuous everywhere. Okay, let's look at the next one. Parabola. So when you see the equation with a 2, and the biggest exponent is a 2, it could go like this. Oops. Y equals x minus 1, 2 with a square. It could be y equals x minus 5, 2 plus 10. You could have a 5 in front. When you see that 2, you go, oh, it's a parabola, which means it's a happy face. It could be like this. It could be upside down. It could be this way. It could be really skinny or really fat, like this. Okay? But it's called a parabola. It's like this is a square, this is a circle, this is a triangle, this is a parabola. Okay? And the parabola is just squaring stuff. So you put something in and it squares it. You put something in, it squares it. So here, if I have y equals x squared, and I want to put a negative 2 in it, what's a negative 2 times negative 2? 4. So if I put negative 2 in, a 4 comes out. If I put a 1 in here, negative 1 times negative 1 is positive 1. So it's just squaring it. What's 0 squared? 0 times 0, 0. What's 1 squared? 1 times 1 is 1. What's 2 squared? 4. So you can see whatever I put in, it just squares it. Okay? So if I graph it, it looks like this. So domain, we say, where does this graph exist on? Domain is x, the x-axis. So because this keeps going up, 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 it's going to use all the x values here. And because it keeps going up, up, up forever and ever and ever and ever and ever, it's going to use all the x values on the negative side. So the domain is everywhere. It exists everywhere. So negative infinity to infinity. Now my range, remember, Range is where does the graph exist on the y-axis. Okay, so range is y. So the graph only exists here, up here. There is no graph down here on the negative side of y. So here the range is only the positive side of y. So it starts at 0 and it goes forever and ever and ever up. So it starts at 0 and goes up to infinity. Now some people have a harder time doing range, so what you can do is you can tip it to the side and you can go, oh, it only exists on this side, it doesn't exist on this side, so it's only here. So it starts at 0 and goes up to infinity. So now we have to, for decrease and increase, we're going to take this little person for a walk, and she always walks this direction. So she's going, whoa! She's going down. For this part, she's walking down. So she decreases from, don't look at these things, she's decreasing from here, and this goes forever and ever and ever to negative infinity. So it decreases all the way from negative infinity to 0, and then it increases, see here, it increases from 0 to infinity because she's going uphill. All right, now is it continuous? Can I draw this without lifting my pencil? Yes. So it's continuous everywhere on the x-axis. Okay, so because we're always thinking on the x-axis, where is it continuous? Everywhere. I can draw it everywhere. Okay, so now let's look at the next one. Oh, it's a parabola too, but it's sideways. So it's just like sleeping, it's tired. Oh, it's called the sideways parabola. Okay, so the sideways parabola, the normal parabola is when it's y equals x squared, or f of x equals x squared, but it's the x being squared. The sideways parabola is when it's y squared. See the difference? X squared and y squared. So, let's see. Oh, we have these weird things here. Okay, let's solve this for y first, and then we'll understand this. So x equals y squared, and if I want to get rid of the squared, because I want to solve for y, I'm going to take the square root of both sides. So now I have the square root of x equals, well, that really cancels with that, and I'm left with y. But when I take the square root of something, I have to take the negative and the positive. Okay? Alright. So, if I just randomly picked numbers, but I picked nice numbers because it's squaring, and here it's square root. Okay, so if I want to take the square root of something, I can take the square root of 5, but it's going to be yucky. It's not a nice number. So, that's why I picked nice numbers, because if I go, what's the square root of 0? 0. What's the square root of 1? 1, but we have to take the plus and minus of it. What's the square root of 4? 2, but I have to take the plus and minus values for here. What's the square root of 9? Plus or minus 3. Okay, so now I graph it. Bloop. Look at this. It says it's a relation. It's not a function. That's the important part here. It's not a function. So what is a function? It's, remember when we did the vertical line test, I can say if I move a vertical line along the function and it touches in more than one place, it's not good. It's not good. So it's not a function. If I look at this one, it's a function because when I move the vertical line, it only touches the function in one place. So this is a function. This is not a function because it touches in more than one place. So it's not a function. Okay? But we still can do the domain and range. Domain, the x-axis. Where does this function exist on the x-axis? It doesn't exist here. Not on this side. It's only on the right side. So it only exists from 0 to infinity. Now the range. Range is the y-axis. Where does this function exist on y? Well, if I just look at the positive side, this is going up, up, up forever and ever and ever and ever. So it's going to use all the y values. On the negative side of y, it goes down, 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 down. So it's going to use all the negative side of y. So it exists everywhere in the y value, from negative infinity to infinity. Okay. Let's look at the next one. The square root function. So y equals square root of x. Really, there's a 2 hiding in here, but we're lazy. This is the one we use all the time, so we just go, oh, if I don't put it there, then I really mean there is one there, but I'm lazy. I don't want to put it there. Okay, so I'm going to pick some nice numbers for x, but because I have to square them, I'm going to pick nice numbers that I can square. So if I put 0 in here, the square root of 0 is 0. If I put 1 in here, well, the square root of 1 is 1. If I put 4, well, the square root of 4 is 2. And if x is 9, well, let's make that into a 9. If x is 9, then when I take the square root, it's just 3. And when, let's say, x is 16, instead of x, I'm going to put 16. What's the square root of 16? 4. Okay. Now, because this is already written this way, I don't take the plus and minus of both sides. It's only because I solved it here I take the plus and minus. Okay. So you can see that the square root is just half of the parabola. Look, it's exactly the same here and here, but it's only half. Okay, so when you have the square root, you can go, oh, that's the same as the parabola, but without the negative side. Okay, so domain x. Where does this function exist on the x-axis? Well, it does not exist here. It only exists here. So it only exists from 0, and because it goes forever and ever and ever and ever and ever, it goes all the way to infinity. Now the range, y. Where does this function exist on the y-axis? Look, it only exists on the positive side of y. If I cover that up, there is no function on the negative side of y. So it does not exist down here, it only exists up here. So the range is from 0, and because it keeps going forever and ever and ever and ever and ever and ever, it's going to use all the positive numbers, so it's all the way up to infinity. So now we have to have our little lady. She only walks this way. She's going for a walk. It's kind of going up. So it's increasing. It's increasing. And we only talk about where does it increase on the x-axis, the domain. So it increases from 0 to infinity. Okay, because she's going up, 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 up. Continuous. Can I draw it without lifting my pencil? Bloop. Yes. So it's continuous, and we only talk about the x-axis. It's continuous from here to here. Okay, all the way to infinity. Let's look at some more functions. Cube. So, cube. You know this is square, and you know this is a cube. If you go to the movies and you wear those glasses, you know what, because the movie is in 3D, you wear the glasses at the movies. So cube is represented by 3D, and that's why we call this cube, because we have a 3 here. But a square is only 2-dimensional. It's flat. It's not 3-dimensional. So a square, so when I say y equals x squared, that's why I call it square, because there's a 2 here. It represents 2 dimensions. And y equals x3 represents 3 dimensions. So this is called cubed. Okay? So this function is called cube. All we do is we cube whatever we have. So if I have f of x equals x3, and I want to put a negative 2 in, well, what's negative 2 times negative 2 times negative 2? Negative 8. If I put a negative 1 in there, negative 1 times negative 1 times negative 1. Well, that's just negative 1. 0 times 0 times 0. But if I put a positive 1 in, 1 times 1 times 1, that's positive 1. And if I put a 2 in, 2 times 2 times 2, well, that's 8. Okay, and if I graph it, it looks like this. Okay, so if I have cubed, it looks like this. Because here, look, I'm putting in a small number, 2, and out comes a big number. So that's why it's reaching up big. Okay, it's getting bigger and bigger and bigger because I'm cubing things. Cubes make things bigger. If I look at its opposite function here, see this 3? This is the cubed root. So if I put a, let's look at 8. If I put an 8 in here, it's asking me what times what is 8. Let me get my calculator. So if I do the cubed root, where's cubed? Cubed root of 8, it's 2. So you can see the cubes makes things smaller. So you can see these are the same shape. This one's just sleeping and tired. It's laying down. Okay, so if I cube things, it makes it smaller. So you can see this, it's not getting bigger fast. It's like, oh, I'm getting bigger but smaller. Okay, I'm getting bigger but not by very much. This is getting big fast because it's cubing. So this reaches up to the sky, and this is sort of like, oh, I'll get bigger but not really. Okay, I'm making things smaller. So if you remember that these two are connected, this one reaches to the sky and this one sleeps. Okay, because everything, it makes it smaller. Okay, so here the domain of this one, it's the same as a line because it goes forever and ever and ever this way and forever and ever and ever this way. It uses both the domain and range everywhere. It exists everywhere on the x and y axis. Same with this one because we've just rotated it. It's still going to go here forever and ever and ever and ever and ever and use all the x's, use all the y's, use all the x's and use all the y's. So the domain and range of the cubing function or the cube root function is going to be the same as a line, negative infinity to infinity. And then let's do increasing. So remember, increasing or decreasing, she only walks this way. So she has to start here. She's going, oh, this is difficult. I'm going up, 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 up. Especially after COVID, we've been a little bit lazy. She's going up, 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 up. It increases everywhere. So it increases everywhere on the x-axis. Let's look at this one. She's walking, walking, walking. It's easy. She's still going up. Up, 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 up. And she's still going to go up, but not very much. So it's increasing everywhere on the x-axis, on the domain. Is it continuous? Can I draw it without lifting my pencil? Yep. Yep. So it's continuous everywhere on the domain, on the x-axis. Okay, so remember these are opposites. They look the same. Okay. Now we have absolute value. That just says make it positive. Okay, these lines on the side just say whatever you put in, put the same number out, but make it positive. So I make it positive. You can't. Well, it's already positive. I can't do anything with these. So if I graph it, it looks like this. Okay. So my domain, well, this is like a straight line. It's going forever and ever and ever and ever. So I'm going to use all my x values. And it's going to go forever and ever this way. So I'm going to use all my x values negatively. So the domain is everywhere. But the range, if I cover the negative side of y, you can see that this graph only exists on the positive side of y. If I do this, the negative side of y, there's no graph here. So this graph only exists from positive up to infinity. Okay? So now we're going to take this little woman for a walk. She only walks this way. Don't look at these. I'm walking down. She's walking down. So because she's walking down, it decreases. It decreases on this side. So from negative infinity to 0. And here, she's walking up. So it increases on this interval. Bloop, 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 bloop. See? And is it continuous? Can I draw it without lifting my pencil? Yep. I didn't lift my pencil. So it's continuous everywhere on the x-axis. Okay. The last one is called the greatest integer function. And sometimes people write it like this, and sometimes people write it like this. This, we're going to do it like this. So you put two lines. I'm exaggerating. I'm making it bigger so you can see there's like double lines here. Okay? And I'm putting here because if you look online and say, what is it? Really, what it does is it rounds any number down to the nearest integer. So what does that mean? I think I have a picture here. Yes. Okay, I want to skip to page 9. Page 9. Okay, because there's a nice example here. So I just drew a number line here. So if here is my greatest, it's called the greatest integer function, right here. And say I put a 3 in. If I put it, no, let's not do 3. Let's do 3.5. If I put 3.5 into these weird brackets that are called greatest integer bracket, so here's 3.5, all it does is it rounds it down to the nearest integer, and a 3 comes out. So if I put 3.9999, which is here, it just rounds it down to the nearest integer, 3. 7.35, okay, well here's 7, and here's 8. So here's 7.35. I round it down, so the answer is 7. 1.1, well here's 1.1. And I put 1.1 in, and it rounds it down to 1. Well, let's do negatives. Negatives are a little funny. So negative 5.9, here's 5, and I get it bigger. Here's negative 5.9. It rounds it down to the nearest integer, negative 6. So it's hard for your brain sometimes to think, oh, down is negative 6. Negative 0.8, well here's half, and so here's negative 0.8. It rounds it down to the nearest integer, so negative 1. Negative 2.5, well here's 2, so here's 2.5. So it rounds it down to the smallest integer, the integer that's smaller, negative 3. Okay, so if I put in negative 2, negative 2, it's already an integer, so it stays negative 2. If I put in negative 1.5, it rounds it down to negative 2. If I put in negative 1.9 or negative 9.9999 right here, it rounds it down to negative 1. 0 stays the same. A little bit bigger than 0, 0.001, rounds it down to 0. 3 stays the same, but 3.9999 rounds it down to 3. Okay, so anything in here rounds down to 2. Anything in here rounds down to 1. Anything here rounds down to 0. So when we graph it, it looks like these little stairs. Okay, so sometimes people call this the step function, because you step up when you're walking like stairs. Okay, so if I look at negative 3, it stays at negative 3. That's why it's a solid circle. But if I look at, you have to make a decision. If I look at negative 2, it stays negative 2. That's why it's here. It doesn't move down to negative 2. I mean negative 3. Okay? So let's look at the domain. The domain is x. Well, can something be negative 1.5? Yes. Can something be negative 1? Can be 1. So if I look at it, all of x is being used for this graph. But range, my y's, if I look at my y's are only integers. Look, if I put in weird things, only integers come out. So I can say my range is only integers. And I put curly brackets because I'm putting like a list of things. Okay? So the range you can see here is only integers. Constant. We either have increasing, decreasing, or constant. And constant means not up and down. So if I take her for a walk, it doesn't go up or down. It's only flat. It's straight. So constant means flat. And it's constant on every stair. So this stair is constant. This stair is constant. So I have to write out each one. But I don't want to write each one, so I put dot, 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 dot. So each stair is flat, constant. Not increasing, not decreasing. So is it continuous? Can I draw this function without lifting my pencil? No, I have to draw, lift my pencil, draw, lift my pencil, draw, lift my pencil. So it's not continuous. Okay? So that's the greatest integer function.